Okay, welcome to our presentation on path optimization for hospitals and houses. Okay, so our question under investigation that we wanted to focus on was how can we determine the optimal paths between houses and hospitals that minimizes the energy required to get there? But this is kind of a broad question, so we wanted to narrow it down a bit. So we decided to investigate a particular kind of house and hospital grid where we assumed that the only way to move is forward and turning. And we thought that this particular question would be helpful in determining where hospitals and residential areas should be developed and how are like the most optimal pathways from getting to a hospital to a house, and how can we reduce the traffic congestions from those traffic that happens. So for each pathway in the way of getting to a house to hospital, the number of ways to get that could be thought of as like the number of permutations based off of the number of rows and columns that the pathway takes in the grid. So thus thinking of these in relation to like a Pascal triangle, the number of pathways can possibly be shown using binomial coefficients. So with this grid like town, then each pathway could be plotted in relation to a Pascal triangle that is originating from a house or a hospital. In this case, we're considering it from a house. And using these coefficients, we can then determine the optimal pathing. So that brings us to our grid town, Talaska town. And within all of our examples, we will focus on a 6x6 grid. The location of each house is unique for each example, but we kept the location of the hospital consistent, that being on a grid point of 4, 4. And within this specific town, the rules of movement are, as said before, they could only go straight or sideways. And we decided to quantify what is like the most optimal route. We wanted to assign each movement a point in energy units. So for moving straight, it's 1 energy unit. For turning, we assumed it would take a little bit more energy, so 1.5 units. And then for an overlap of another pathway to the hospital, we said it would take 2 energy units. And then for overlapping and a turn, we said it would cost 2.5 energy units. With these restrictions and assumptions on this town, we needed to develop our algorithm for the number of possible pathways it can take to get from a house to a hospital. So the first step in doing so is to count the number of rows and columns from the house to the hospital. And then you can create a unique Pascal triangle for the house. And then using that Pascal triangle, we can find the number of diagonals in which the destination it takes to get to the hospital. And then from the starting point, we can then use the number of possible, or we can calculate the number of possible pathways by either using the number of rows or columns and then doing the diagonal, choose the number of columns or rows to get the number of possible pathways.
In our first route example, we explained all the possible pathways to arrive at a hospital located at coordinates 4, 4 from house 1 located at coordinates 0, 0. To arrive at hospital, we have to move at least 4 times sideways and at least 4 times downwards. With that, we make a total of 8 movements. And we can arrange them either way to find all possible pathways, in other words, which can be returned as 4 sideway movements, possible ways of arranging 4 sideway movements in 8 slots, and after that arranging columns in the remaining spots. This results in the formula of 8 choose 4, which is 70. Therefore, from house 1 to hospital, there are 70 possible routes. The route from house 1 to hospital also creates the familiar pattern of Pascal triangles. In terms of Pascal triangles, the hospital is located at the 8th diagonal and is in the 4th row and the 4th column. Therefore, according to our algorithm, the possible pathways would be diagonal choose row or column, which becomes 8 choose 4, which is 70. In our second example, we find our second house located at coordinates 1, 3, and it blocks both horizontal and vertical pathways for house 1, as our town condition states that no pathway shall overrun the house. Due to the restriction, the coordinates surrounding the house would only have access in one possible direction from the previous opening coordinate, making the possible permutation same as the previous coordinates. This will cause a shift in pattern of triangle, and we would need to create a pattern by adding 2 terms above it, The pattern will lead us to a total of a 54 possible permutation from house 1 to hospital while avoiding house 2. In terms of formula for pathway to avoid, we would have to subtract the total pathways from house 1 to house 2 and pathways from house 2 to hospital. Therefore, our total pathways from house 1 to hospital comes out to 70, and we will subtract 16 from that, which results from 4 pathways from house 1 to hospital and 4 pathways from hospital to house 2, therefore resulting in 54 pathways from house 1 to hospital.
So in certain scenarios, it is impossible to create unique paths without overlap. In these cases, we assign a penalty for overlapping edges, and in doing so, we can minimize overlap while maintaining the restrictions on how our paths are developing. So for any given grid with homes and hospitals, each path has two valid moves, moving downwards or towards the hospital. This means a home on the left of the hospital can move down and right, and a home on the right can follow a path down and left. As such, all paths must necessarily converge at either 2 or 3 edges adjacent to the hospital. This allows us to determine the minimum amount of overlap so we can approach that amount when applying our own algorithm. For n houses and m edges from which houses can approach, by the pigeonhole principle, taking the floor of n over m will give us the minimum number of paths that are in any given adjacent edge. Subtracting 1 from this then will give us the minimum amount of overlap. So now we can develop the actual algorithm. Proving that the algorithm is exactly optimal is beyond the scope of our project, but we can logically build a heuristic with low complexity that guarantees minimal overlap. So first, our application of the pigeonhole principle will allow us to know what degree of overlap we are aiming for. Based on the restrictions, applying our determined formula will give the minimal overlap achievable. Since an overlapping edge has a higher energy cost than the energy cost of a turn, as we prioritize low overlap over more turns, adding turns to reduce an equal or greater amount of overlap is always optimal. So therefore, we should always add turns until minimal overlap. And finally, we can set a parameter p that is equal to the maximum number of turns allowed for a certain set of paths being considered. This does not mean that all of the paths will have p turns in them, but in the worst case scenario, a path will have p turns in such that they are minimizing overlap. So we can begin with p equals 1 such that, or even p equals 0 in the case that the houses are at such a point that they can just follow one direct set, but then move to p equals 1 so that each path can have at most one turn. And then if there's overlap that's greater than our minimal overlap, we can continue increasing p until we have reached the minimal amount of overlap.
So in this example, we have 4 houses, and the houses are located at 1, 1, 1, 3, 2, 2, and 6, 1. And we have the hospital at 4, 4. Now, to find the optimal pathways from one house to the hospital, we have to first find the Pascal's triangle for each of the houses. In this example, we have the Pascal's triangle for the greenhouse, and we can see that the total amount of pathways from the greenhouse to the hospital is 4. If we repeat this procedure for all of the houses, we find that the red house would have 4 paths, the yellow house will have 6 paths, and the blue house will have 10 paths. Now, we also have to find the associated energy units for each optimal path. So for the greenhouse to the hospital, it will be 7.5 energy associated with the optimal pathway. For red, it will be 5.5 energy. For yellow, it would be 6 energy, and blue would be 5.5 energy. Now, if we take a look at the other pathways for the other houses, all the houses. So if we take a look at blue, for example, if we go down this path, we actually encounter some overlap, which isn't what we want because that would be more energy that we have to use. So in this case, we would want to try to avoid this and try to find a path that avoids all overlap. And in this case, we found one that avoids all of it. And another example would be green. So if we go here and then we go down, we encounter overlap, which isn't what we want. So in our original case, if we just go right 3 units and then down 3 units, we actually get the optimal pathway to the hospital. So how can this algorithm be used? Another certain scenario we can use this for is actually school buses and school. So for a school bus, we want the school bus to go to all the not all the bus stops, but as many bus stops as possible for all the kids. So in that case, we will want to allow school buses to go down the paths. So in this case, the bus stops would be counted as the houses and what we have in our example. In that case, we want the school buses to go to the bus stops. So yeah, so in that way we could try to find the optimal pathway from bus stop to the school. Can this algorithm apply to towns with less restrictions on movement? It could. For example, in the image that we have here, we could find the maximum amount of pathways from point A to point B. In this case, we actually have to work backwards because it might be a little bit more difficult because we have rectangles in this problem. So if we work backwards and we find that we find the pathways from B to each vertex, we find that for the upper left corner, we find that the sum of the lower left and the upper right would equal the upper left. So if we do this for all of the pathways and the vertexes, we find that we have a total of 28 maximum pathways from point A to point B. And this, this is for rectangles as well. So we could apply this. We apply this to towns with rectangles and squares. And also we also talked about three-dimensional grids. So in three-dimensional grids, we have X, Y, and Z. And in that case, I believe using Pascal's triangle would be less intuitive because it would be harder to calculate the pathways, but it's possible to use permutations and combinations to find the maximum pathways from one point to another point on the XYZ grid.
And that concludes our presentation. Thank you so much.